Okay, we're good. All right, this session is a special session that's I considered optional, although I see a number of people here that really want to hear this whole story. Earlier this year, I started experimenting with some things that takes advantage of the fact that the sensors, the digital sensors, the silicon sensors, are highly linear devices. So when you have images you're collecting of very dim objects in the sky, you're going to have the true linear sum of the light from the light pollution and the object. So I reasoned that it should be possible to remove the light pollution in part, albeit you'll get a bit of noise left over, and get an object. And the images that you saw in the last session of the Orion sword were my first attempt at that. I did it with that because it was a very bright object. I could have 2-minute exposures at ISO 200, and it was encouraging. I did the stacking. I got, you saw the gradient I had. I could pull the gradient out, and I got a halfway decent image. I thought, great, I'm on the right track. So I went to the Rosette Nebula, took 2 hours worth of images. That's 30 images at 4-minute exposure, ISO 200. Did exactly the same thing, and I got junk. Absolute junk. If I looked really hard and I held my mouth the right way, I could see some evidence of an image in there, but it was useless. So I spent a lot of time doing some analysis. To go from this to this requires that you need to know a great deal about what that light pollution is in terms of how it affects the image. I thought it would be just good enough to stack a bunch of these things and subtract it out. It clearly did not happen. Okay? So here's what I'm showing. The problem is that you're going to have, in this case of the Rosette Nebula images I took, out of a scale of 2 to the 16, 16-bit image per color, 15,000 units are light pollution, and 500 units are object. That's quite a challenge, but it's linear. So it has to be possible to do something like subtract just in between the two, leave a little bit of light pollution behind, but get rid of most of it. The light pollution is going to have noise in it. So it's going to affect the desired image to some extent. And there's nothing you can do about that if there's enough noise in the light pollution. I haven't gotten far enough into this game to really know what that impact is yet. But the things I did find out are what I'll describe here to give you an idea where to start. Keep in mind, this is a project in progress. What I learned on these experiments is useful, but is not the total answer to how to solve this problem. The one thing that's evident is that the linearity of the sensor is what the key is. Figuring out how to get rid of the noise and the light pollution is yet another problem to solve. Okay? So, I created a synthetic light pollution object. I called it NGC 0000. Okay? Doesn't exist. It's on a dark sky. It's very faint. Both the sky and the object have noise added to it. It's Gaussian noise. This is all done in Photoshop. Okay? So I had a highly controlled image. Okay? So then I created a light pollution image, which I actually extracted from the NGC 2244, which is the cluster that comprises the inner part of the Rosette Nebula. And so all I did here was apply a Gaussian blur with a very large radius. I got rid of all the stars, any evidence of anything in there, except it preserved the light pollution. You can see in this image that there's a bit of darkening in the corners.
Yeah.
Okay, my first thought was that was caused by the fact that I did not bother to take darks, flat fields, and bias image. because I didn't know what I was going to get. I didn't want to waste the time. In retrospect, that was a mistake. I went back, of course, to the Orion Nebula stuff, which I did have darks, flats, and biases. And I went back and did all those corrections and looked at the resulting calibrated images. There was still a gradient in there. You saw it in that image that was stacked. That gradient had nothing to do with the camera. Okay? It's a mystery to me exactly why the light pollution behaves that way, but that's real. Okay? If anybody ever figures out why that's so, please let me know. Okay, so squint your eyes just right. There is the light pollution with the object added to it. Can you see it?
Yeah.
Okay. You should be able to because it's a perfect square and it's a contrasting color with the background. So you should see it. If that were a diffuse image like the Rosette Nebula, it'd be a lot harder to pick out. But you know it's there. It's just added linearly. So then I went through this extraction process that I was working on and did some measurements. Here's the object. This is a surface plot. There's a program included in the DVD that's called ImageJ. It's a piece of software that was developed by National Institute of Health for people doing microscope imaging for biological purposes. And it does neat things. It has a lot of interesting image analysis tools in it, one of which is this interactive surface plot. And it gave me a very graphic view of what it looks like with the noise and the object's noise in the image. Okay, you can't see it so well in the top view of the image, but it is pretty significant, and that's what the problem is. And here's that same image added to the light pollution, and you can see what's happened here. There's a good deal of curvature here. Well, I have a little bit of a trick here because I expanded both ends of things so that it would accentuate it. But the fact is, that's real in the image. So now if I take the original light pollution image, which I can extract by methods I'll describe, and subtract it out, there's the object again. Now if you look at it closely, you'll see there's a great deal of noise both in the background and in the object itself. That's noise left over from both what's in the object, because this would correspond with a single sub-exposure. Now someone asked me, what do I mean by sub-exposure? It has nothing to do with the darks and flats and bias images. It has only to do with the fact that you need to accumulate enough dark image data in your deep sky image to average out the photon statistics. Photons are arriving with some statistics. It's a Poisson distribution. If you take a single sub-exposure, and you'll see what that means in just a moment, it'll be extremely noisy. And that's because not enough photons have arrived to complete the image itself. And so it looks very noisy as a result. So that's a sub-exposure. It means that in this case, when I show you the Rosette stuff, I took 4-minute exposures at ISO 200. I took 30 of them, okay? So 30 times 4 minutes is 2 hours. So the actual exposure effectively was 2 hours. The sub-exposure is simply an element of the process that's involved with averaging out the noise in the image. Okay? If you could take a 2-hour exposure on a CCD or a CMOS imager, you would saturate the blazes out of all the star images, but you would get the nebulosity the way you get it by the sub-exposures. Sub-exposures are an opportunity to be able to get the object and the stars without having the stars badly bloated out. Okay? So in a way you have control over both by playing this game. The other reason is if you don't invest huge amounts of time in a sub-exposure, if somebody comes by and shines a light at your telescope or a plane flies through and destroys your exposure, it's not a great loss. So this is all working for us. The fact that the sensor is linear, you can add up images to get the equivalent of a long exposure, is all a plus in every respect.
I'm sorry, once again, what is the sub-exposure?
The sub-exposure, let's say, for a very faint object in the sky like the Rosette Nebula, you need at least 2 hours. Longer is better, but at least 2 hours of exposure time. And what you do is you select a sub-exposure time. I selected 4 minutes in this case, such that the light pollution did not exceed about 1/3 of the scale of the imager. In a true dark sky situation, the sky, whatever you want to do is reasonable. I know people who've taken 10, 20-minute sub-exposures of deep sky objects in a very dark place. So that's okay too. The longer the exposure, the greater the chances you're going to have a satellite fly through or an airplane fly through. I tend toward the shorter exposures to reduce the probability of having too many sub-exposures destroyed by terrestrial objects or orbiting objects, okay? So it's a game you play. And you have to decide for yourself exactly what you think is necessary to get your images. My experience has been 4 to 6 minute exposures, maybe most 8 minutes. It usually gets what I want. But it'll depend upon your particular equipment, your quantum efficiency, that's a big driver, and what aperture optics you have. The bigger the aperture, the more photons you collect, then you'll increase the exposure that you get. Trouble is that's F ratio dependent, and so there's a bunch of trade-offs there. For example, if you have an 8-inch aperture at f10, you're not going to buy anything by having an 8-inch aperture because it's spread out over an f10 cone. In other words, a very small number of photons are falling on individual pixels relative to what it would be if it was an f2. If you use a hyperstar on a celestron, it's an f2 optic. It's going to have about 400 millimeter focal length. Now you're in business. Your exposures can truly be short, and you'll still get good stuff. Okay.
And you take over that. How many of those 4-minute sub-exposures, or whatever time sub-exposures?
Well,
to stack.
Well, you want to get as many sub-exposures as you possibly can get, as far as your patience will allow, as far as where your object is in the sky. In my case, in my backyard, my field of view is about like this in the sky. It's about an hour and a half before and an hour and a half after the meridian. I can get in 2 hours with a meridian flip on the mount. And if you look carefully at the Rosette Nebula, or the NGC 2244 images that I gave you on the DVD, you'll see I labeled them east and west, meaning where the scope was relative to the mount. Okay? When you go through the stacking process, you'll find, if you watch it carefully in DSS, you will see it rotated one image 180 degrees after a certain point, and it continued to do so. That's because it's matching star images, and when it got past the meridian, it had to rotate 180 degrees to match up. Okay? That's the price you pay for crossing the meridian. The other price you pay is whether you have the cone error in your telescope taken care of. Let me tell you something, it is worth the effort to do that. It reduces the complexity of making your meridian flips. It increases the probability that you'll get everything lined up after the meridian flip, and you'll have a lot less trouble. And I've done that with every setup I've done, with the exception of the stupid thing I had for the dark sky session, and I didn't bother to do it because I didn't have enough time. So getting rid of you know what I mean? Do you know what I mean by the cone error? Right? No? So, yeah. The optical axis of your telescope must be perfectly perpendicular to your declination axle. That presumes, of course, the RA is perpendicular to the deck. That may or may not be true. It probably is, but it may or may not be true. So you can fix it for the declination axis by putting your scope at the top of the mount, point the pole finder scope at a distant object, get the crosshairs on something recognizable, and then shim your telescope until it centers up on the same reference point that you have on your polar axis scope. Now that presumes the polar axis scope has been aligned too, which it usually is out of the factory. Once you do that, then when you do a meridian flip, your object will be within a few arc minutes at most of where it was before, after the meridian flip versus before. Okay, so it's worth the effort to do that. It's a nuisance because it takes about an hour to 2 hours to do it, and you have to go and buy a pack of metal, usually brass shim stock. It'll cost you about $40. You'll have enough shim stock to fix everybody's telescope in the club. So it's worth the effort. Okay, enough on that. This thing clearly pointed out I can make a synthetic deep sky image with a lot of light pollution, with a lot of gradient in the light pollution, and I can pull it back out again. Okay? So, let's go and take a look at what's required to do this. Obviously it's DSS, which you already have. I'm going to tell you Photoshop is the only thing that's going to work right now. When GIMP can process 16-bit per channel images, GIMP will do just as well. Don't even bother with this in GIMP. You're going to end up with a total mess at 8 bits per channel. So don't even bother. If you can't do that, don't even bother the deep sky and light polluted skies until you have the capability of processing 16 bits per channel images, because you're going to need every bit of it to get this to work. ImageJ I included in your packet in the DVD. That's the tool I use to analyze the images and find out what sort of problem I had to deal with. And I strongly suggest that you spend time to learn how to use it, because almost certainly you're going to get into a situation where you're not sure what you've got. And the only way to find out for sure is to do some of the operations I'll describe in just a minute. Okay. This, by the way, you'll understand that in just a minute, measuring the light pollution level. Okay, so key assumptions. I'm just going to reiterate this. Image sensor is linear. That you have to set your sub-exposure so you don't saturate anything that contains the object itself. You can saturate a few stars, that's fine, but stay far away from that point. And I found that if the light pollution peak is about 1/3 of the total dynamic range of the sensor, you have plenty of headroom to play with. Now for something like the Orion Nebula, you're going to come close to saturating that trapezium area. And that's a different problem. Extracting light pollution from an object photographed of that nature with a huge dynamic range, it turns out to be a bit of a problem. It's easier to do the Rosette than to do the Orion Nebula. And you saw some of the basics of that last week when I was extracting out that gradient. Remember, I was doing some editing on the levels of the overexposure that was in there. And that you can do, but it's not very well controlled, and it's something that we have to work on. ISO 100 to 200. If you want to stretch it, 400, but I suggest you stay away from it, because it'll only give you trouble. Again, exposure to keep the light pollution between 30 and 40% of maximum, closer to 30% rather than 40%.
How do we know the maximum? That I didn't quite understand.
What, this one?
Yeah.
Well, what you have to do is do some experimenting. Let's say you're going to do this in your backyard. You're going to go out there, point your telescope at a bunch of stars. You don't even care whether you've got an object you want to photograph. Just point it at a bunch of stars, take some 1 minute, a 2 minute, a 4 minute, an 8 minute exposure and see what you've got. See where the histogram is on your camera. If the histogram is mostly confined to the lower third of the dynamic range on the histogram on your camera, that's the exposure you want to use. Okay? You don't need to go to ImageJ to do this. Usually cameras will give you the histogram on the display. Figure out how to use it if you've never used it, and use it. It can tell you very quickly where you are with this kind of stuff. Okay, I already said that the order of 4 minutes for very dim objects is necessary. Not much more than that for a light polluted sky, because you're going to run out of dynamic range if you do. This number is based upon my optics, which is a Teleview 85 with a flattener compressor to give an equivalent 480 millimeter focal length. Okay, it's an f5.6. So roughly any optic that's f5.6 will be wanting something like 4 minute exposures. If it's faster, you want shorter. If it's slower, you want a little bit longer. You'll have to find that out on your own with your own equipment. There's no recipe that I can give you that tells you what you must do, because it will vary with your sky conditions. In fact, your sky conditions are going to vary from minute to minute, as you'll see. Maximum dynamic range of the camera is absolutely critical. Again, that's why we have the ISO 100 to ISO 200. It keeps you away from the saturations that occur in the various stages downstream from the sensor. You want to take advantage of the maximum number of electrons per pixel that you can have, so you can get a chance at getting this stuff extracted. Again, I'm going to tell you, for most things that are very faint, if you're going to do this from a non-dark sky area like your backyard, you're going to at least need 2 hours of exposure time. That's what happened with the Rosette Nebula, and I suspect you're going to find that with everything. Again, experiment with it. If you decide that's not right, well, make it right for yourself. Don't listen to me, just do what works for you. Okay? And this is the critical point. Assume light pollution is time variable. That was the shocker. I didn't realize that was an issue, but after I looked at it and thought about it, I said, well, of course it is. Okay?
Time variable in what sense?
Right here. Okay? I used ImageJ to measure the green channel median value for the entire picture, the entire sub-exposure, all 20 megapixels of it. Okay? Now, taking the median means that the stars are going to be, and the object itself contributes a constant value to the image, to the median calculation. Yet it will be a small effect because it's a small part of the light pollution itself. Okay? So this is a pretty good measure of the light pollution brightness itself over the entire sensor on the average, or I should say median-wise. And you know what the median is? 50% is above, 50% is below. That's what it means. Okay? So, I started my sub-exposures here. There's 1, 2, 3, 4, 5, and so on. Notice I go from 28,000, 25,000, what is it? Yeah, 28,000 to 22,500. It's dropping fast, and this is over a period of 20 minutes. Why would it do that? Think about it a bit. I was in a winter sky, or roughly early spring sky when I did this. When you have sunset occur, the air cools rather rapidly. Okay? Moisture in the air starts to fall out. Scattering of light diminishes, and I believe that's what's happening here. Okay? And then it starts to flatten out. That was my particular circumstance. Who knows what you'll get? At this point, meridian flip occurred. My drive automatically does a meridian flip. I don't have to tell it to do it. It just says, when it gets to a certain point, bing, it goes. I lose a sub-exposure there because typically it happens right in the middle of another one. Okay? From here to here, I am reacquiring and recalibrating PhD for the guide star. Okay? I started the guiding here, and here's the first exposure. I waited for the guider to stabilize. This is something you should get in the habit of doing. When you finish the calibration on PhD, you're going to start guiding automatically. Watch the curves. Initially, they're going to be rather ragged. After a while, it'll settle down. Then you start your sub-exposures. Okay? Don't get in too big a hurry because you'll waste a sub-exposure or two. So again, the image is still diminishing in brightness. It gets to the bottom, and then it turns around. Okay? Right here is when the moon hit the horizon, coming up. Okay? So instead of continuing down, which is what I expected it would do, it starts to rise again. Again, the moon's coming up, it's starting to contribute to the light pollution, and that's what happened here. Now, why this went down, somebody turned a light off, God knows what. That's probably what happened. But look at the scale here. The bottom is about 19,600, and the top is about, what, 23,000? And the object's 500, I estimated. If I stack all those images, no wonder I got garbage. Because I was averaging all this change of light pollution into that whole mess. So that was the clue that we had time variability that was a real problem. And the degree to which this is a problem in your particular backyard situation will affect what you get. You will have to find out on your own. You should do this analysis yourself before you commit much time to any imaging. Because if you find this is wildly varying over time, you may not even be able to do anything, depending on how things are. And I can't go any further than that on that because I don't know what other contributing factors are to the time variability, but assume there is time variability.
So if you go out around midnight, your neighbors should have finished flipping on off and on their backyard lights, hopefully?
One would hope. One would hope, yeah. And the malls usually shut down, but they don't turn off the parking lot lights, so that's not going to matter. Fewer cars driving around with high beams on. I'm sure, some of these wild variations here might have been.
So you want non-variability to be able to more precisely do your subtraction of that?
I don't think it matters. As long as you don't have a huge variability within the sub-exposure. Let's say we have what we have with this Rosette Nebula, 500 data numbers above the noise, if you will, for the object. If you have a variability within the exposure of 2,000, it may compromise your image. It may not. Because remember, it's additive. So whatever happens in your image, the object is still sitting on top of it. It should not matter. That remains to be proven by experiment. So remember, this is a first time thing for me. I've never done this before. I never even thought it was possible. And it surprised the heck out of me. I gave myself 1 chance in 10 of this working when I started this project. The only thing I knew for sure is the sensor was linear. I knew it had to have some basis. All right? Having figured this out, then I could go at the problem seriously. Again, if you, in ImageJ, you click on Analyze and Measure, you can generate a table like this. The other thing I usually do, and I don't show it here, is I include 2 more columns, the maximum and minimum. And I do it for the green channel is usually good enough. If you were curious to see what it looks like in other channels like I was, do all 3 channels. You'll have to switch to different images in ImageJ because it separates the channels individually. Yes, sir?
So does this take the CR2, the raw images directly?
No, you have to convert to TIFF. I tried it. It doesn't know what to do with CR2 files. I'm glad you asked that question because I forgot to mention that. And then there's this other thing, that's the surface plot. You go to Plugins, 3D, Interactive 3D Surface Plot. That is the slickest tool you can imagine. One peculiar thing about it is sometimes the first time you try to use it, it crashes. In other words, you bring up the surface plot, it'll come up with a big long list of error messages. You just click those off, go back and start this over again, and it works. For me, it's worked 100% of the time, the second time around. I don't know what's going on, I don't care at this point. I can still get what I want. Okay? Now, I don't know if it, well, let me do something here quickly, just to give you an idea what we're dealing with here. ImageJ is a multiple platform tool that you can play with this yourself to experiment with this. You can literally put the mouse on this image and grab it and rotate it around and look at different views of it, as you'll see in a minute. Okay, so the summary of what it takes to extract this image from the light pollution is you open a sub-exposure in Photoshop or in ImageJ when it gets to be reasonable. You duplicate the image, so now you have a copy of the original image. In the copy of the image, you do a Gaussian blur with a 250 pixel radius. Now that number is not magic, it can be somewhere in that vicinity, but you want it a big number. So it can average out things without starting to clip the gradient in the light pollution itself. You dim the image a little bit with curves, excuse me, with curves. You subtract the blurred image with its dimmed from the original image. That gets rid of most of the light pollution. I say most because you dim it on purpose in order to prevent removing some of the object data. You're left with a little bit of light pollution and a little bit of curvature, that is, a little bit of gradient. You can fix that later. It's usually pretty small and not much to worry about, okay? So, you get essentially an image with light pollution removed, and this dimming process causes an offset, which you can subtract out later after you stack the images, okay? So here it is again. In Gaussian blur, you type in Photoshop 250. In GIMP, there is a slider or a up-down arrow, or you can type it in there too. You go to Duplicate, Filter, Blur, Gaussian Blur, set the radius, click OK. You go back to the original image tab after you've done this. Okay? So now you've got on two tabs the original image and the Gaussian blurred image that's been dimmed. Okay? Or you're about to dim, excuse me. The dimming process involves going to Image Adjustments, Curves. You get this control window. You put your mouse on the dead center. Get this number and this number to match it, 128. Or make this one 128, make this one 108. That dims the image. The exact number is not critical. I found this to work rather well for what I just did here. You may find something will work better with more or less. You need to experiment. Okay? So once you've set this up with this curvature, you've dimmed the image on the average. The endpoints are unchanged, as you can see. You click OK, and you've got a dimmed Gaussian blur. So now, with the original image tab selected, you will now see the original image on the screen. You click on Image, Apply Image, and you get this window pop up. In this window, there's a source image. That's your Gaussian blurred and dimmed image. Okay? That's going to be the source to subtract from the original image. You click this down arrow and select Subtract. Okay? Once you've done that, you click OK, and you're going to end up with an image with the roughly most of the light pollution subtracted. So, looking at the original image, this is what you see. Whoops. This is the Gaussian blurred image. You'll see a little bit of shading here because I converted it to 8-bit images. I found out something with OpenOffice in this presentation tool. If you have big images, it gets into deep trouble. So these have all been made into 8-bit images to show up without having trouble. So that's the Gaussian blurred dimmed light pollution image. That's after I've subtracted it, okay? If you look really hard, you might see a trace of the nebula in there. You know. I took that image, this is from a single sub-exposure, and stretched it. You can see there's something there. That's promising. In fact, that's exactly the kind of thing you would get if you were in a dark sky. Okay? That this image here is what one subexposure would look like, even in a dark sky. You might see traces of what it is you want in there. But you know that after if you stack everything and then stretch, as we talked about last time, you will get something. I stretched this, and this is a good example of what I mean by the photon noise. Notice how noisy that image is. It's terrible. But 30 of those images averaged together, you get something more attractive. Okay? So, let's look at ImageJ just momentarily. Talked about the measure. This surface plot is what you see here. If I brought the right images with me, I would have been able to show you what it looks like. But here's the Gaussian blurred image. Okay, go back again. This is the original image viewed in the surface plot. Most of this stuff up here is star images. Okay? This is the baseline or curved surface of the light pollution, and in there somewhere is the Rosette Nebula. Okay? So now this is where I've Gaussian blurred everything out. Here's the subtracted image where I've subtracted the light pollution image from it. Now watch this. If we do the subtraction, we still can't quite see the image in there exactly, but you can sort of see something happening here in the stretched image itself. Okay? Keen thing about the interactive 3D plot, you can turn everything around and look down on the top of the image, down from this point of view. You can actually see the image. Okay? So, it's a very powerful analysis tool to help you figure out where you are. The other thing that you can do is there's a bunch of sliders around in the interactive 3D surface plot. And there's a slider that's for smoothing. If you set the smoothing number to 20, you can get approximation of what the Gaussian blurred image will look like. So it kind of gives you an idea what you're dealing with. If you got a bunch of bright stuff in there like we have for the Orion Nebula, it's going to show up in here, and you're going to know that you're going to have to deal with that in a special way. Okay. My experiments with the Orion Nebula was I went through and did the Gaussian blur on it, and I took the Gaussian blurred images and edited them so that it followed this overall curve to get rid of the bright portion of it, like I showed you last week. Okay? You do that with every one of the images. Real pain in the butt. But I tried it to see what would happen. It brought out a great deal more of the dim object fields in the Orion Nebula. So it's worth doing. So, where are we? We use Gaussian blur to create a rough measurement, and it's rough because it has some of the object in it, of the light pollution itself. And for bright objects, we clone out the bright regions, and that's a matter of judgment. You're not, there's no recipe for that, but use your judgment. Obviously, any pretty image we get from this whole process is for that purpose only. There's no scientific value in it. You've destroyed more data than you can ever recover in all this stuff. Okay? You dim the thing with curves, you subtract the modified Gaussian blur image from the original, and you repeat the process for every sub-exposure.
Can you do it with a script? Can you write a script?
I haven't done that yet. Yes, I think you can.
Well, that would help a lot.
Well, it would save a lot of pain, yeah. It only works if you have something like the Rosette Nebula where there's not a lot of bright stuff. Yeah, I don't know that you can do a script to clone out the bright regions. You may be able to, I don't know. This is something that's worth exploring as we go along. This is why I keep saying, let's have a special interest group in this club where we can talk about methods from time to time and see what everybody's come up with. Maybe we can all learn something from this. Okay? After you've done all this stuff on the sub-exposures, now you can go through the align and stack like we did last week. Okay? So that's basically the thread of this thing. Now, getting back to image calibration. On the Rosette Nebula image, I had given myself such low probability of this working, I didn't bother with the dark field, the bias images, or the flat field images. I figured there was a lost cause anyway. If I got anything, it would be so noisy as to be useless anyhow. Okay? I didn't bother. So then, as I went back and looked at it, I figured, no, this stuff is stuff that has to be done. This is fixed noise contribution from the camera. It has nothing to do with the light pollution whatsoever. You've got to do something about it. The bias, of course, is the read noise. The dark is the thermally generated noise in your camera. And the flat field removes dust, shadows, and vignetting in the lens system that you're using. You must do this. The problem was, I couldn't get DSS to do that without manipulating the pedestal on which it sits. So if you discover a way to shut that down, I'd be interested in what it takes to do that. Because you cannot allow anything to be done to these images once you've started this process of removing the light pollution. If they go through and do this calibration, and then at the same process during the calibration removes the pedestal on which it sits, you can't get an accurate measurement of what the light pollution was. You've got something else. It may be possible to make that work, I don't know. What I did in my early attempts ended up being useless. So that's an area to explore. I'm sure that some of the expensive tools, will allow you to do the calibrations without, cutting the pedestal off. I believe there may be a way in DSS, but I haven't found it yet. A program that's less expensive is Nebulosity. The same guy that did PhD also did this stacking tool. It's pretty good, and I'm pretty sure that can turn. You can set that up to turn off the background subtraction, which is what they call it typically. But I have yet to discover how it gets done in DSS. Okay. Most importantly, there is no cookbook that I know of here, at least yet. Now maybe we can come up with some way to produce some kind of a script in Photoshop to do the light pollution subtraction for images that have very dim features in it. That's probably easy to do. Something like the Orion Nebula or any other object that has a huge dynamic range. For example, M31 has a huge dynamic range. I'm sure it's going to present the same problems that M42 has, and there's a bunch of other objects in the sky that'll have that same property. So the problem needs to be solved somehow. And I'll be working on it, and I hope you will be too, because I think this is an interesting endeavor. I think we have a chance of being able to do at least some deep sky imaging in a light polluted area, even though the images that result are not as good as we'd get in a dark sky. But it's fun to play with. Okay, so the things you need to know is the amount of light pollution has to be measured. The color of the light pollution is an issue. You have to keep in mind that it's going to influence the color balance of your image. I'm not sure how to solve that problem at the moment. I'd hate to think of the possibility I have to go through not only each sub-exposure, but each channel within each sub-exposure and subtract this light pollution. I don't even want to think about doing that at the moment. I got reasonable color balance in the Rosette Nebula. Okay, maybe I don't have to worry about that. Time variability is a big issue. Fast changes during sub-exposures may or may not be a problem. Something we need to discover in future experiments. Again, brightness range is a problem. I strongly recommend you keep a detailed log of everything you do in your backyard experiments. I do that all the time. I do that because I need to know what PhD is doing. And if I change something, I make an entry in my log. Make sure I don't forget that I've changed it. Because sometimes if you're watching the guiding curve and it looks a little funny, you can bump some of the parameters a bit and stabilize things. Okay? Usually you do that before you start your sub-exposure, but sometimes I've been tempted and foolishly made changes, and sometimes it works and sometimes it doesn't. But when you do things, keep a log of what you've done, so if you see something funny in the final images, you know you've done something that may have affected it. Okay?
Some of these video cameras have a night mode, which actually shoots in kind of a greenish light.
Uh-huh.
You could actually put one of these on a tripod and just turn it on and talk to it.
Yeah,
I don't know how good that would be. Notes would be better.
I think I'd rather keep my notes rather than high-teching. I'm an old school type for that. Okay, keep an eye on sky conditions when you're doing this. Sometimes it'll be obvious something has changed in the sky, and you really need to make a note of that. Yes, sir.
Comment a little bit about, using something like a light pollution reduction filter.
I used it in this image, by the way. This is the IDIS LPR filter that you get from HUTEC.
So even with that, you still got.
Well, you saw what I got. If I had shot it without it, I don't know what I would have gotten. Because I sucked out all the non-essential bands in the visible spectrum with that filter. And if I had taken it full bandwidth, I don't know whether I'd have been able to do this or not. So I have a feeling that's a requirement, but I don't know. I've yet to run that experiment without the filter, which I will do at some point.
Don't you get the effect of that the filter changes like the color balance?
Oh, of course it does. I've calibrated that. I know how much color balance error it creates. I've got a little sticker on my monitor that says when I'm doing the LPR filter, these are the numbers I need to diddle in Photoshop to fix it. Okay? Oh yeah, it makes a difference.
That was a really bluish.
Nah, it does all kinds of weird things.
Don't you compensate for that when you're using these sky stacker? You just shift to the.
Well, that's exactly what it was doing there. You saw it in that image from M42. That's exactly the shift that this thing causes. It suppresses a lot of blue because it cuts off sharply after all the interesting stuff is gone, somewhere around 400 nanometers. Okay? It won't let any UV through, it won't let any highly scattered blue through. In fact, it cuts off most of the stuff that is in refractors images where the deep violet is out of focus. It cuts off that image altogether. So if you got a refractor that's not exactly the best apochromatic lens, that filter will cut it off. There's other filters you can buy that'll cut that off too, but the LPR filter is very effective for that.
So this isn't really light pollution. I guess you consider the one on sky glow. So
Sky glow, even at Lockwood Valley, there's enough sky glow from the cities to represent a contrast problem for your deep sky images. I have not done things there recently enough to know if the gradient is a problem. I suspect not, but I don't know. We'll find out. So I'll be imaging out there another time and we'll find out whether this is a problem. The LPR filter for sure will improve contrast out there, because most of that stuff is scattered light pollution. A lot of it has strong emission lines in it from the sodium and from the mercury and so forth. In the case of LED lighting, that's becoming popular. There's a strong ultraviolet line at about 390 nanometers, thereabouts. The LPR filter cuts off that completely. So it's not a problem. It is a problem for environmental purposes because it affects any creature that depends on essentially the UV portion of the spectrum to navigate. If you got a lot of pollution from the LEDs, that's a problem. That can be filtered out, by the way. And some companies are recognizing the need for that and are doing it. So, one of the things I have been doing is I've been watching my neighbors' backyards during exposures, and if I see something change back there, I make a note, because I know that's going to have effect on this time dependency. And I'm going to slowly begin to build up information on what's causing the time variability, whether it's close-in stuff or it's just stuff far enough away that I have no idea who's doing what. For sure, it varies because of the different amount of transparency over a period of an hour or two. Transparency will vary during the night as temperatures drop. Any questions? That's all I've got for this.
I'm going to talk about the special problems and some of the corrections that you can do for urban imaging. So my comments are actually good for visual and imaging people. So some of these are general. Some of these may be surprising, and I forgot one prop that I was going to bring with me, but that's all right. You'll know what it is when I describe it. By the way, this is already written up as an article for the website, so I'm hoping to post it there in the next week or so after I fill in any corrections I did here. Now, your number one, your biggest and your mortal enemy when it comes to urban imaging is this stuff. Now actually this doesn't show one effect that I wanted to show, but this is all what I call direct lighting because you can see it. And I don't care if it's way back there. Those photons are reaching your eyes, they're reaching your equipment, and believe it or not, even if you take certain precautions, you may not be able to defeat all of it, but you can certainly trim it down by a lot. Direct lighting is this guy down here because I can see the light, all the lights here. Now, that's your number one problem. Number two, actually it does show up right there. That's indirect lighting. That's a reflection. Could be off haze in the sky, could be off of a building, could be off of a tree. You want to avoid all sources of that for reasons that are going to be obvious in a moment. But your first option is, okay, it's a little bit off, but your first option is turn the damn thing off if you can. All right, yes, I know you want the comfort of not having to use a flashlight in your backyard, but let's face it, that direct light is going to decrease the magnitude at which you can see down. And for planets, that won't matter. For their moons, it definitely will. So you have to make up your mind. So all the stuff about direct lighting, indirect lighting, and stuff like that probably doesn't apply if you go planet imaging. Certainly doesn't apply to everything except Pluto. So they're all very bright. Even Uranus and Neptune are bright enough to video image. And therefore, if you can video it, you probably don't have to worry about any light, direct, indirect, or whatnot. But if you are worried about it, your first option is turn it off. Talk to your neighbors, trying to get them to cooperate. I live in a 14-unit townhouse. I made a deal with our president that as long as I gave everybody in the complex 2 days warning minimum, I can shut the outside lights. And that helps an awful lot because we recently installed brighter lights. And I couldn't, the only astronomer in the group, I couldn't argue against it. I says, all right, fine, but I still want to be able to shut them off if I give fair warning and when I want to. And he said, fine. And nobody's complained about it so far. My next door neighbors aren't as good. You can shield yourself. You can actually use buildings. Actually, once I turn off the townhouse lights, the townhouse itself is a very good shield against some of the lights that I encounter, which is the apartment complex next door, which won't cooperate at all, certain street lights, anything. So, yes, and does that introduce limitations? Yes, but I'll get to that in a second. Patio or pool umbrellas, they work. Remember, if you could see the photons, your equipment can see the photons. See? Now, of course, direct lighting may be a little easier to get rid of. You just have to drive around something. Indirect lighting is a whole different topic. There's not much you can do about that. Believe it or not, this works. for the visual observers, and to some extent maybe the imagers, but that's up to you. But certainly for visual observers, that cuts out on a lot of light. See. Yes, some of this old stuff, yeah, but some of you may not be aware of this. Your open truss tube, photons are hitting your primary directly, even if it's indirect. Photons are hitting your secondary indirectly. Cover it up. And now we'll get to, hopefully, yes. The bottom line is any source of direct lighting, even if it's at an angle, like suppose you're pointing your tube this way, the light's behind you. You're saying, well, it can't possibly enter the tube. Photons are incredibly sneaky, and you can't trust the little bastards. You've got to shield. You've got to shield it. I'm saying this humorously because that's my usual modus operandi of talking. But believe me, I couldn't believe it. The little bastards are sneaking in from the sides, and it just, and now we come to this thing. Some of you may think, oh, what do I need a dew shield for? It's so warm. Maksudovs, refractors, and Schmidt-Cassegrains. That big lens or whatever at the front, stray light comes in the side, your camera might see that. But I recommend this for Newtonians. Now you may think, well, come on, Dave, the primary is all the way down at the bottom of the tube. Yes, I knew that. But fortunately, I kept my old dew shield because I was still getting a stray light phenomenon. I put the dew shield on, it went away. And I'm looking around going, what's going on here? And it suddenly occurred to me. The secondary. So this is the tube, and here's a secondary, right? Light might bounce that way. Light might bounce in this way. Remember, glow is all around you. It's like a radiation source of which you are in the center. It's like being in the center of a plutonium bomb. You're surrounded by plutonium. There's nowhere to go. And I guarantee you, no matter how much you think you're not going to catch a stray piece of radiation, boy, you're going to catch a stray piece of radiation. So yes, I routinely, on a Newtonian, use a dew shield, not for the primary. Primary is too far down. There's also this to think about. Unless you've got like velvet or flock coating inside the tube, I don't care if it's painted black. Still a chance of reflection. And remember, did you say go several minutes at least to capture some deep sky objects?
It's a problem.
That's going to be a problem. Guess what? Yes, those photons are trickling in. But if you put a bucket under trickle, you step long enough, it fills up. You have to do something. Now again, for planetary observers, that's not a problem. You got other problems, which I'll get to. Now, I talked about indirect lighting. How can you minimize that? As I said, you can try and use a building to shield some of it. The bigger the better. Hopefully not an office building that you keep lit up 24 hours a day for some strange, stupid reason. But you could try doing that. But I used to use my parents' backyard back when I was about YA4. I didn't realize at the time, but street light. Couldn't see them. No street lights in the backyard. That thing got dark. This was, of course, before Rosemead, used to be called South San Gabriel, got really urbanized, and now that backyard is probably not the way it used to be. But back then, that was all you needed. But it was an urban setting. Now here's where we get to the interesting things where you think, oh, Dave, but you're limiting what I'm seeing. Yes, I am, but what choice do you have? Where's the least amount of light pollution generally? Straight up. Why? Further you go down this way, you look into more haze, generates more light. Look this way, thinnest part of the atmosphere, least amount of haze. And if you don't believe me, I'll show you two photographs that show what happens when that happens. You can also, this sounds silly, but don't look in a direction where the glow is, which I violated one time, and I'll show you that example a little later. But in other words, just be smart. Limit yourself. Remember, this is urban. This is not dark sky party night way off in the boondocks, okay? Then these limitations somewhat lift off, although from what I hear from Lockwood, you guys got a problem in the southern region. If you go to Ford, you're looking right over Hesperia, Victorville, and Barstow.
Yeah.
So it's like, there's always a direction, unless you get way off in the boondocks, like in the middle of Australian outback, where, and even then you'll find people living out there. So see, you can't get away from it entirely. This is controversial, believe it or not. And it's still controversial with me. Filters can help. They can help with certain objects, because some objects glow only in very restricted bands of light. So planetaries is one. Stars don't really count, because stars being pinpoints of light, they're easy objects to photograph, which is why open clusters and globular clusters are relatively easy to photograph even from urban locations. Done it all the time from Griffith with so many cameras and telescopes, I've lost count. So those are the three primary objects. Diffuse nebula, you're getting into that realm where every unit of sky has a very low brightness value. But you could try. That's the other thing I'm going to hit upon. Just try. Because we're amateurs. We're not going to be killed if we didn't get the photograph that's going to prove dark matter or dark energy, right? We're not in it for that, right? We're in it for the enjoyment. And part of the enjoyment is to discover what you really can do with your equipment. But galaxies, I find, are the iffy topics. Why? Because their spectrum is more spread out. Different types of stars, gaseous nebulae, dark lanes, all sorts. They're more spread out, so they're less helped by filters. But the only thing I could tell you is the only way you'll know is just experiment. Go back and forth and experiment and see what happens. But I found that they have helped for the three objects I've listed: planetaries and both types of clusters. So other helpful items. He's going to start laughing, because if he remembers me, remember back in the old days of the JPL Astronomy Club, I hated go-tos. I said, that's not real astronomy. I'm eating my words now. Because from an urban location, it's so bad now, you're lucky if you see second mag stars. Some nights it's lucky if you see first mag stars.
Barely see Jupiter.
And barely see Jupiter. So now, on those nights, maybe you'll say, I give up. But even on those nights where I barely see the Big Dipper, I can still do imaging. But I can't find my objects. Even Messier objects, most of them, unless I have a go-to mount, because it's really, really, really tough. Which, by the way, is the other lesson. Even if it seems like it's not a good night, if you can see second max stars, give it a shot. Even if you see first max stars, some objects are still within your field of view. Of course, the easiest way to do a go-to mount is if you have it connected with your computer. I'm not sure if Vance touched upon this thing, but it's really nice to have everything done right here. There are nights where, and I'm going to get to one of those points, there are nights where I have not left the laptop. Once I have everything set up, it's...
Yeah,
so how do I
do it all the time?
So how do I find and use star charts and planetarium programs? But finders, well, telerads are limited use because you just can't see too many stars. Finders, you can always see more stars, but that's problematical from urban location, unless you use this trick, which I started using. Because your guide scope these days is an 8x50 finder. Well, it's actually not 8 times because there's no magnification, but it's a 50 millimeter finder attached to with an auto guide attached to it. But if you continuously take video, guess what? You now have a finder that reaches down to 10th mag, even from an urban location. I've seen them. And that makes matching stars much easier. So you can use this as a finder. And of course, it's a wide field of view. It's 1 or 2 degrees. If you need more of a field of view than that, I can't help you. Because you should at least have the go-to get you within half a degree, at least, of where you're pointing. And if you haven't quite figured out how to do that, well, ask around. There's plenty of expertise. Now, I'm not sure if you touched upon this, but I find this very useful. Usually with a star chart program, what? North, east, west, and south, right? Wouldn't it be nice if you just wrote, unless your telescope mirror images, in which case you're up the creek without a paddle. But most telescopes, like Newtonians, Maksudovs, refractors, you can rotate the field of view to match north, east, west, and south. Now with a mirror image view, you get north and south. But now you got to remember east and west are inverted. But now you can match star fields directly. And boy, is that a big help for finding objects. Because even when you're off-pointed a little bit, you really need to move the thing around and point it.
Your guide camera software typically will allow you to do reversion if you have a mirror image.
Yeah, but I typically just prefer to rotate the camera.
Well, I'm talking if you have a reverted image as opposed to a rotating image.
Well, if it's a mirror image, then you really do have to flip it by the camera because there's no other recourse. Because I'm not sure you're familiar with this, but a mirror image view can never be rotated to match the original view. It just isn't possible. So that will flip left and right, I would agree with. But north and south, I would move the camera and get it. By the way, it's always consistent. If you're always consistently using, your equipment in an equatorial mount, you could just set it up once, make sure and make a mark right there. Now you just put back on the mark every time, and it's upright view. You don't have to be precisely north, but you have to be close to north, south, east, west that you can compare the views. And by the way, determine your field of view. By the way, I use the camera I'm imaging, deep sky imaging with, as a finder because it's 18 arc minutes across. And how do I know that? Various ways to measure that. You can use star drift. What I do is just a cheap, dirty way. I compare the view with a view from the STSCI space DSS view, which is north, south, east, west. I just compare it and measure it from there. Because you can always call up those images to be 18 or 20 or any width you want to up to a degree. And the thing about it is that now you compare it directly and now you know pretty much exactly within 10% what your field of view is. But that's very important if you could compare star views on your chart. Because nothing's more frustrating than knowing just how big is that star field you're looking at with your camera and where does it relate to to your star chart program. Because there are errors and go-tos, unfortunately. They're not quite state-of-the-art. So you're going to have to use your star finding tricks, match a star field up, and then figure out, okay, I got to move this much. Now, some deep sky objects are bright enough, you'll actually see them in both the finder and your deep sky camera on a 1 second exposure. Those really blow me away because then I know I got this one nailed. 10 seconds, 15 seconds, 20 seconds, I got the image already. If it's that bright on a 1 second image, you just see it. What can you do? Okay, now we'll get to the easy topics, the planets and the moons. I highly recommend you use a video camera. I know some of our friends like Dave Pinsky have used DSLRs. They're okay, but if you want sharper views, or any view at all in some cases, you need to take video because you need to stack not tens or hundreds or thousands, but several thousand images. It really is necessary, especially on a night like tonight where the marine layer is moving in and I could see Saturn. See how I'm shaking my hand? That's the width of Saturn. I could literally see it doing that.
That's not counting the wind either.
Yeah, that's not counting the wind either. No, there was no wind tonight.
Do you prefer a color video camera or black and white with color wheel?
I prefer a color video camera, but that's because I'm an advocate of single shot color. I figure, you know what, it's hard enough in urban imaging to get the subject to steady down, the tracking to steady down, to everything to steady down, plus the fact that Jupiter is rotating at a good clip. So I can't afford, that's my personal opinion, I can't afford to switch the color wheel, take another set of videos, no, I'll capture all colors at once. That's my humble opinion, and but that's the type of imaging that I do. Keep the weight of the thing down. I've known some guys that take a big fat video camera and honker it on their telescope. God knows how they balance that. God only knows. So, but and these days, with web cameras or the equivalent thereof, there's no need to get a big fat camera. Web cameras are more than adequate because you're not storing the thing in the camera, you're storing it in the computer. Because if you step on the camera after a night's work and all the video is on there, man, you're going to cry. So don't do that. You do have to experiment with shutter speeds. Even if you think you know what's right for a planet, depending upon the conditions and so forth, you're going to experiment with shutter speeds, brightness gain, contrast gamma, and the whole nine yards. Because ideally, and this is my personal opinion, you've got to take the best raw data you can get your hands on, because there's only so much you're going to process out in post-processing. And that, my experience has really caused me to believe that. But your number one, in this case, the sky glow is at least your worries with planets and the moon and so forth. That's your big enemy. If you don't believe me, go up to the dome and look through the refractor. It's really horrible tonight seeing. Now, because that is a single frame, and the other frames weren't any better than this, from 2015 on, I believe, January 23rd, if I remember the date right. There are 3 shadows in this image. There also happens to be 2 moons. One is Callisto, which is fairly easy to spot. I can't see it. This is the entire video looked like this. So I didn't think anything was going to process through. But I take 2-minute videos because I prefer a couple of thousand frames so I can select a couple of hundred frames. And yes, the seeing is going to blur the view. But you do see something. This is processed from that video. Now, look back on the original one of the frames.
I'm good there.
Maybe there's something there, but that could have been some other defect. And it shouldn't be looking like an O. See? So we weren't and nobody saw anything that night. He saw something for 30 seconds, but that was about it.
2 seconds right here.
But Io shadow, Callisto shadow. That's Europa's shadow. It's right at the edge, so, thanks to seeing how blurred. That's Callisto right there. That's Io right there.
All 4.
Yep, all of them. And that is not the red spot. Like I said, the reason I can tell, because north, south should have been down here. Don't see it. Now this next one is both an impressive image and a cautionary tale. This was taken during the 2003 Mars opposition, which blows this one away by a considerable degree. But still, this is a little over-processing. But I did that because I wanted to see just what details you could get with a 5-inch, I think it was a Maxudo at the time, but it might have been my Schmidt cast. Crises region up in here. Yes, the colors are saturated. See, this is the other point. If you wanted a realistic view of this thing, it'd be low contrast, very low everything. The whole thing of imaging is to increase your chances of seeing details. And if that means it's unrealistic, let me clue you in. There hasn't been one realistic image of the sky published by professionals or amateurs. They've always been exaggerated, and I certainly exaggerate a lot of mine, because the idea is to see features, not to be scientifically accurate. Well, maybe in the case of scientists, it should be scientific accuracy, but they rarely do. Now, you're not limited to just those. However, I must warn you, this image was taken with my deep sky imager only because I was deep sky imaging that night. This is from Griffith. You should know this planet because that's Oberon, that's Titania, and there's Ariel right in below. That's Uranus.
Very nice.
By the way, these little spikes, they're called diffraction spikes. They're caused in the Newtonium by the spider veins. Now, I actually prefer those because you can actually use them to focus. Very briefly, you go to a much brighter star than this until you can see the spikes. You will know you're in focus on a traditional Newtonian when these spikes are a single line. Why do I say that? Because if you're out of focus, they do this. They split apart and they come together and sharp when you're in focus.
Like a rangefinder.
Pretty much. Pretty much. And in the sense that once you focus it, you're focused at infinity. You're not focused beyond infinity or in infinity or somewhere in between infinity, but you're focused at infinity.
What optical tube was that?
This is a 10-inch. This is my 10-inch reflector. But you don't need anything that big to photograph. These. I wish I had a photograph of Saturn, but I'll let you know right now. Through a 5-inch, I have with a sensitive web camera, I photographed down to Rhea and Tethys. Those are 11th mag objects. Those are really faint. By the way, just to show off, this is Neptune, and yes, that's Triton right there. Nereid is somewhere in here, but that's 20th mag. And for urban imaging, that, see as my hands don't leave my arms. Yeah, that's probably tough. But I just want to show off this one too. Asteroids make fine targets, but because they look like stars. There are 2 asteroids. Can you guess which ones are the asteroids?
The bottom right?
The brightest stars in the field.
Okay.
I think Vesta and Sirius.
Ah.
This is 18 arc minutes by 14. Just was able to
You were
fit
lucky
it.
to get
But
it
when,
in there.
yeah, but when I first looked at this image and I compared it, I said, what are these 2 stars doing here? You know, I found these stars. I said, what are these 2? And then I suddenly realized that dummy, those 2 are the asteroids. So you'd be surprised. Sometimes they're very bright. Now I'm not going to cover comets because A, I don't have a good image of a comet myself, and B, everything that I say about galaxies applies to comets. So we'll get on to that.
Dave,
Yes.
those 2 asteroids, how far they were?
I don't know.
Earth.
I don't know that night. You have to look back. That was last year. I don't know.
You were lucky to get them that close together.
Yeah.
That
Yeah,
was
that's
the amazing
very
thing
rare.
that's the amazing thing.
Yeah, the 2 tracks did this.
Yeah, that's amazing. to get
Yeah,
them close
that's
together.
rare. You usually only get 1 asteroid at a time, and that's not going to happen for quite a while. Now, for deep sky stuff, obviously you need longer exposures. For the planets, if you're using a web camera, the best you can do is what, 1/5, maybe 1/2 of a second. That's maybe enough to do M42, but not much of anything else, the very brightest. So you need longer exposures, which means in my books, and this is again just my opinion, you need cool CCDs to get the longer exposures because that beats down the noise. And the noise that you're actually seeing is the sensor noise, because the sensor is trying to warm up. It's like any other electronic device, but they're usually sensitive to their own infrared signature, which means they're actually, I'm seeing myself. And that adds to the signal. The longer exposure you take, the more heat builds up and the more fog. So you do need cool CCDs if you want to take longer exposures. Now for me, and I know this makes me controversial, but I think stacking is a limited value. It works for planets because videos you could take hundreds and thousands of images. But for single exposure, that's a little tough. And the noise level is beaten down by it's either square root of n or 1 over the square root of n. I think it's square root of n. So initially there might be some gains, but the gains start to get less and less and less and less as you go further along. Because do the square root of n, and you can see that's actually happening. But should you not do stacking? No. If you think that's the only way you're going to get longer exposures, you better go for it. And I have tried it, and sometimes it works and sometimes it doesn't. But the best thing I can tell you is, and this is my theme here for urban imaging, go out there and try. I don't care what equipment you have, just do it. You'll learn. If nothing else, you'll learn your limitations of what you can and can't do, and that might guide you into where you need to invest your equipment. Because the worst thing you can do is be an absolute neophyte, and I've seen 3 of these guys on the internet. Absolute neophyte, never operate or touch a telescope in his life. Goes out and buys a C16 computerized mount with a 3,000 baht ECBIS camera, and then asks us on the bulletin boards, "Can you help me?" And of course, the first question out of my mouth, because I don't know anything about this guy, is, well, what kind of astronomy experience do you have? Oh, no, this is my very first telescope. I've never even operated any telescope before. And I said, Rod's a ruck, and just sign off, because I can't help a person like that. They think technology is going to help them. Technology is not going to help you. The experienced and wise use of technology might help you, but that's all you're going to get. Now, as to what you can do, taken last year, this is a 2-minute exposure. Why does it appear so pristine? That's when I took it. Zenith. Shut off all my external lights. Still had my neighbors shining on me, but as long as I had the dew shield and pointed straight up, background glow wasn't that bad. It really wasn't that bad. Now, but this is a relatively bright object. This next one is notorious because it seems like it should be bright. It's listed at magnitude 6, but believe me, it's not that bright. Why? Because M101, the pinwheel, is notorious. I think they made the magnitude estimate out of just that little speck, and they forgot to notice all this junk around here. This is, let's see, I didn't list it, but I think this is a 6-minute exposure. And I can see on the original image, maybe you can't, but there's a little bit of glow back here. Again, straight above. Nothing I can do. See, so for some objects, 6 minutes, that's the limit. And why can't I process this out? Once again, the sky glow, notice it's the same general color. So how's the computer going to differentiate these spiral arms from this? Very tough.
Hey,
It's very tough, yes.
so these are single shots?
Yes, these are all single shots. No, these are not. Again, these are all taken with my 10-inch.
With a CCD camera.
Yes, cool CCD camera. It's the Orion G3 single shot color, and then an Orion 10-inch f4.5 Newtonian. Okay. Now I mentioned that stars are good objects. They certainly are. One thing I like about star clusters, no matter which ones they are, is that with black and white image, you can't tell what the colors are there. That's part of the charm of this thing. I saturated the colors, okay? Again, I'm not going for realism, but there's a nice spread of colors throughout here. They're not too much. There's a couple of whites, but a lot of reds. That's a hot pixel, by the way.
I was
didn't
just gonna
process it
ask
out.
that.
Yeah, those are hot pixels. I didn't process this out. This was actually taken from Griffith. Some of these images are taken from my backyard, and some of these are from Griffith during public star parties. So yes, you can do that. And that is M3. That's taken from Azusa. And that is a 60-second exposure. Once again, the star colors is what you're probably going for if you're going for clusters like this, because they're very hard to see visually, because most of these things aren't bright enough to trigger color vision. In fact, the only time I can recall, I think it took a 30-inch before I started seeing color in M13. It had that weird effect of giving it a three-dimensional structure to it. Of course, the 60-inch is great. But even from urban locations, I said planetaries? Sure, why not this one? Again, take it from Griffith. By the way, I know it was darker back then, but back when I was a 10-year-old lad with a 50-millimeter refractor, I did see this object through it. Of course, I waited till it was almost overhead, but
Griffith has a lot of light pollution.
yeah. And yet, even under those conditions, well, yeah, you're looking over all of LA. I mean, what can you do? But you can still do an awful lot.
There is one nice thing about Griffith. Every now and then we get good stable skies.
Yeah.
We do get stable, and that helps.
Yeah. But you can't always defeat sky glow. Hopefully this next one will appear as good there as on the monitor. It appeared well. Nothing you can do about this thing. Notice the color of the galaxy. This is M81. And notice the sky glow here. Why all that sky glow? I was impatient. I couldn't wait. I couldn't wait till 3 o'clock in the morning. So I said, let's just do it. See, again, just try. And this reinforced the belief that, just basically, in a narrow cone above your head. But remember, as the year progresses, more objects come in, and you're not limited to M objects. I've caught a lot of NGC objects. Unfortunately, I don't think I included one in this slide presentation.
Yes? Is that a single image?
Yes, they're all single images.
Single exposure. Okay.
I don't stack.
Okay.
One reason why is because of of anything can happen, like the Marine Air move in with the clouds and kill the whole expedition. So I figure if I have any shot to take a single exposure, also single exposures in general tend to have better signal to noise ratio than
What was the exposure time on this one?
6 minutes.
6 minutes.
Yeah, and so there's nothing you can do about that.
What kind of mount is this? What kind of mount?
It's just an equatorial mount. It doesn't matter what the mount is, but you do need a tracking mount.
Yeah, I understand, but I was just curious.
EQG from Orion. See, that's why I'm not making this technical. So I mentioned my equipment, but it really doesn't matter what the equipment is. It really doesn't. I've done a lot of work. It's low quality now these days. And I don't post it, but I did a lot of work with 5-inch instruments, 5-inch C5, 5-inch f5 refractor, and a 5-inch max pseudo. This is the biggest scope I've ever owned, and I've only owned it in the past couple of years.
And it's an 8-inch, you said, or
10.
10-inch?
Now, if you wait patiently, yeah, you can get a decent image. Now, the original, there's still sky glow over here, but it's very, very faint. And yes, to get this thing, I used the technique that Vance mentioned, which is a Gaussian filter. So that most everything, including the two galaxies, was blurred, but it kept the general sky glow, and just subtract one image from another, and then a little bit of more processing here. Not bad, considering that this camera is only 750 by 580. It's a medium format camera. It's not high def. All right, took shorter than I thought. So the bottom line is, I don't care what equipment you have or what you want to do, try. Now, unfortunately, I'll add this much because I do have a little bit more time. I don't have a slide of this thing. But generally what I do is if this patch of the sky, up here, generally I'll operate on one side of the meridian or the other because it's a German equatorial mount, and unfortunately the stupid thing wants to flip over when it reaches the meridian. So I either have to time it so it doesn't hit the meridian before I end the exposure and go on to another object. Things are continually moving in this direction. So it's a conveyor belt. So you just have to go like a half strip here and keep going. But I'll scan from one NGC object after another. And actually, why don't we do it? Why don't we do it? Wait a
Try
second.
it.
Yeah.
Try.
Give it a shot. Wait a second. But you never heard of this one, NGC 40. It's in Cepheus, which is probably why you never heard of it, because there's just nothing in Cepheus. I mean, either you need a very large, wide format camera, and what you're seeing is diffuse nebulae, very faint on top of that. So it's like from an urban location, it's like, or they're very large, sparse, open clusters. I mean, if you look at the NGC list and you see images from the DSS images, it's like boring. There's nothing there. And so when I first started this thing, I said, I don't know what's going on here, but let's see what's going on. And I came across this weird guy.
Gordon.
That's a planetary, and that's the real color. Wow. That's what shocked me. In fact, I confess, the first time I saw this thing, the first thing I checked was my color balance, because I thought something's got to be wrong. But then all the stars turned out reasonably okay. They're yellowish, but so I took another image. I rechecked the color balance. That's the correct color.
Do you know what the name of that thing is? I think we saw that through the 60s.
I think it does have a nickname, but I don't know what it is. It's NGC 40.
Campbell's.
No, it's not Campbell's. It's not Campbell's star. Yeah, no, no, that wasn't Campbell's star. I double checked, and the guy says, no, NGC 40 is something else, and he added it to the list because obviously this would make a good target. And notice carefully, there's some weird structure here, and inside the nebula. So what that might look like through the 60, I mean, that might tempt me, if Cepheus is directly above, to join that night and go take a look at this visually, because this is very odd. The only thing I can imagine here is that the usual planetary are doubly ionized oxygen, which is written O3. O1 is not ionized. O2 is singly ionized. O3 is doubly ionized. And all that means is singly ionized, one electron flew off and is dancing away someplace. O3 is two electrons did that and probably dancing around the space someplace. Yes?
The popular name is NGC40 is bow tie nebula. Well, you can argue that's
It's like red blob to me.
well, that's like the crab nebula. I've seen so many photographs that I've never seen a darn crab.
Like a bow tie.
But let me finish this thing. So usually you see green or bluish green, because typically what you see is hydrogen beta of all things, and O3. But my guess is that for some reason, maybe this is an older planetary or something like that, but when the excitation goes down, or it wasn't very big to begin with, then what you see predominantly is hydrogen alpha, which would explain that color. Because this can't be a continuum because of the nature of planetary nebula. So, and this is not the only one. I wish I could remember the other one I found that was red. But this is what happens when you don't go looking at your favorite objects again and again and again and again. If with a go-to mount and with a deep sky imager, even from an urban location, you could just go from one NGC object to another. And so you might pre-select them with the DSS images, which are available on the internet. But they're lousy indicators for a couple of reasons. First, they're black and white. Second, they're really overexposed. And but they do have the advantage, they'll tell you how big the thing is. So if you know what your field of view is, you can set the website to generate a field of view identical to this thing, so you can tell if this thing is worthwhile, if it's too big or too small. Yeah?
I have multiple questions. Did you use filter in this case?
Yes.
Okay.
I've only been using a filter for a year. This is 2015.
Okay. Second question. How can you make sure that this one doesn't get overexposed?
You take multiple exposures and you keep trying.
Third question. Can you explain the configuration of planetary nebula? Why do we call it planetary?
Because originally to Herschel, and a lot of them are no bigger than that, and that's a star. They look like small planets. Remember, Herschel named these objects. This was long before photography.
So just arbitrary.
So he said they look like planets. Now he knew they weren't planets because they weren't moving. So he says, well, they look like planets, so let's call them planetary nebulae. They're planet-like nebulae. And that's just very straightforward description.
They're round.
Now, do they have any relation to planets? No, probably not. But you know, a name is a name is a name, and most of these things are very small. At this resolution, they're as small or smaller than that halo around the star. So beware when you go planetary hunting. You're gonna get a lot of images of disks that are bluish green. See, and that's what you're gonna get a lot of. But some of them are surprises. Now, can you pre-filter it? Yes, and even I do, because I don't want to waste my time looking at the stuff that's way too small or way too faint. Like, for instance, the Palomar globulars are off my list because they are way too small and faint, and both sometimes. The Terzon globulars are the same way. A lot of opens are either way too big. You know, they'd extend out to here on this image, so they appear very sparse and contain no structure. Or they're a little tiny smudge that's about 15th mag, and I'm not kidding. They really are, some of them really are that faint. So my usual thing to do is to do a survey list. First you go to the NGC IC project list. It's available free on the internet. They have an object list generator for you. You can generate by types of objects or by constellation, or both. And I frequently use that to generate a list which is in text format. So all I have to do is copy and paste it over, and then I go through, and sometimes these are like over 100 entries, depending upon what you selected, and go through, and first off, I eliminate those that by the description. They give a size, a magnitude, and all that. I first eliminate those that are beyond 15th mag, because even though the magnitude estimates are lies, in my opinion, because look at M101, so it's a 6th mag, and that's obviously just a central region, but it gives you some idea how bright they are. So I cross off them, I cross off any that are too small, because they give the angular size, and then I go down the rest, and I look at the images. And that's how I know that both the magnitude estimates and the size are lies, even to today. But it's a good way to make an observational list, and then you go about and do it. And believe me, you're going to photograph the same object again and again and again. That was my 3rd image of the crab. It's still my best, but I still know I can improve upon that. And this one I can improve upon that too, yeah?
And then your filter, I assume, was a Rosette filter, right?
It was a, what do they call it? It was a Lumicon filter. They call it the deep sky filter. It allows only 3 bands of light. One of them is hydrogen alpha, one of them is the O3 band, and the other one's the hydrogen beta band. Now, guess what? If you look that up on the spectrum, red, green, blue. But I'm not sure. I might go filterless from here on out. I think your biggest worry is trying to keep stray light from those pesky little photons from somehow squirreling themselves into the image and doing like the M81 image, doing that to them. But, again, experiment, try. Go back and forth with the filter, see what happens. Your best bet is to photograph the same object, remove the filter. Yeah, may have to refocus. Remove the filter, photograph it again, and see what happens. It's pretty close to the same conditions, right? So you have a relatively unbiased test. But I think with galaxies, you're better off without the filter, because there's no way the filter, and remember, the filter is going to dim down the light and increase the exposure time. So you're fighting that too. Do you take a 4 to 6 minute exposure with the filter, or you take a 2 minute exposure without the filter? And just keep trying and keep piddling with the equipment, because one size doesn't fit all, and that's why my talk is really not that technical. Because I found that, yeah, you can get into the technical part of the thing, but the real thing is that guess what? I hate to say this, but you won't know until you go out there and try. And then you'll find out where you're making the mistakes, and you'll improve your technique. But, as I said before, at various talks, what's the advantage of urban imaging? I don't need to go to an outhouse. I got a real bathroom. I don't need to sleep in a tent. My house is right there. I don't need to worry about draining batteries because I got AC. See, a lot of things you don't have to worry, and I don't have to drive 3 hours out of my way, haul the equipment out, haul it back into the car, haul it out of the car. I just need to haul it out of the garage and haul it back in, whereas I store it anyway. So for me, going to a dark site, yeah, there a couple times I'll do that per year because I don't have a southern sky. My townhouse blocks that. So I basically photograph to the north. North is completely free, and northwest is completely free. But, there are a lot of objects there. There are tons of objects. And right down to Orion. I can photograph M42 from my location. Just barely. So that's my southern limit. But there are a lot of objects in that great big band. And if you want those other objects, better find another site.
NGC 253, get that one, baby.
I did.
You weren't at your house, right?
Oh no. What makes you think I was at my house when I did that? Oh no. That
thing's pretty far south.
Yeah, that's for the
Joshua Tree or
no.
your other one?
Borrego Springs, Nightfall.
Nightfall, yeah.
Has a good southern sky. Let's see. I'm not sure if this is the most recent.
No.
Would be better.
No. I don't know.
Actually, it looks better here.
Yeah.
This thing, for some reason, has an orange cast that thing doesn't. Actually, I see purples in this image, but this is orange cast here. And the galaxy actually faintly extends all the way there. I can just see it
bigger
way down
galaxy
there.
than that, yeah.
Yeah. This barely fits in my field of view, but I always take another exposure again because you can always improve. Your equipment might have improved. Your techniques might have improved.
Your 10 inch is a 10F what?
4.5. It's short.
4.5, so 40, okay.
Yeah. Yeah, that's a fast, relatively fast instrument with not too much coma. Besides, the camera's not big enough to see the coma region, so that explains that. But yeah, you asked for it, you got it. Visually, I have seen this thing as a faint oval with the dark bands cutting across.
Yeah,
like
it's a beautiful
this.
thing visually.
It's
Gorgeous
weird.
visually.
Even though you
Yeah.
know what it's supposed
Yeah.
to look like, I let my eye and perception go, and yeah, it looks like a very faint, even oval with a bright spot in the middle, and then I see these bands traversing it like this dark bands, which is not what you see here. It's weird. But there's a lot of things that, and this is why I continue to do some visual work. There's a lot of things that your visual impression is going to be really, really different. So it's worthwhile taking a look every now and then.
Is because of non-linear sensitivity in our eye?
Just because the eye is different from a camera. That's the best way I could put it. The eye is always different from a camera. Yep.
Why we see the big stars on the picture?
That's because with a fast instrument like that, stars are going to blow it up the longer you photograph. If you want to avoid that, you go with a long focal length instrument. But eventually, what kills you is whatever it is in the train. And I forgot to mention one thing, by the way. Thanks for the reminder. Anything in the train that will diffuse the light, including any sort of dust, oil, something on the optics. Remember, you're going very deep, so that anything that spreads the light as it enters in your telescope is bad news too. So you either live with this or do otherwise. I've just learned to live with it. In fact, that's why I got a 5-inch f5 refractor. The guy said, "You're nuts. That's not a photographic instrument. You're going to have halos around all your stars." Yeah, I want to see that. I want to see blues and red halos and yellow halos. That I consider photographic, and I still do to this day. See? So it depends on what you want. If you want accuracy, then you're going to go one route. If you want, pretty pictures, you go another route. If you want to see stuff that you're never going to see, even through the 60-inch, because of narrow field of view or unavailability, what are you going to do?
Why?
This opens especially for deep sky people. This imaging opens up the urban environment.
Well, I see it. I see your point of view and his point of view. What we need to do is kind of get
No.
It's
It's a
good.
good.
We can get good star images.
There's no issue here.
There's no issue. What I'm
There's no
saying
issue here. It's one,
yeah.
It can do it both ways.
Yeah.
It's a different set of assumptions and a different set of
Mhm.
priorities, and there's nothing wrong with that.
Yeah, I know what I'm saying is
Yeah.
use the stacking. Like you go through the stacking, go through all of the imaging. Can you do it here? That's
Sure,
what
but he
Sure you
chose
could.
not to. There's
Huh?
nothing wrong with
Yeah.
that.
Okay. Well,
I chose not to. But if that's your only option, go for it. Or if
Try
that's the
it.
option that you like, which is even better. If that's the
Like you
option that
said,
you like,
try
go
it.
for it. Just try it. Make up your mind yourself. There's not too many things that are cast in concrete. Can you do deep sky imaging with a web camera? I've heard of guys trying, but they're limited by the fact that the noise builds up very quickly. So these same guys pretty soon say, "Oh, I got a cool CCD camera." Told you so.
That's the exciting thing about
That's
this.
why I have both cameras.
It's an evolving
Yes.
technology.
And that's why I have both cameras, because this deep sky camera doesn't work with beams on any planets. And I can't use my web camera on deep sky objects. I've tried it in both directions. And it's like, that's the real separation, not between me and Vance. That's, to me, the real separation. The technology is not there yet to include both in a single camera, because it adds weight and unnecessary power and expense to cool a web camera when you're doing planetary work. And on the other hand, you need cooling and everything for deep sky work, but then the camera is not suitable for a video. Typically, you gotta. Right now, he's correct. The technology is now divided. Maybe one day they'll merge. I hope they do, because I hate operating with two different cameras. Because if, like at Griffith, I got to make up my mind. Do I go see planets or do I go see deep sky? Because everybody else is seeing planets. I can offer deep sky, which you will not believe how many oohs and ahs. One time I spent my time hunting around Sagittarius. So M7, M20, M22, M17, and all those nebula there. Yes. Were they trail? Yeah. I couldn't help that. But I still got a bunch of oohs and ahs because the people, you can't see those any other way. And I told them, yeah, if I popped an eyepiece there and I tuned down the contrast till it disappeared, that's what you see. You just won't see it. So I have to make up my mind. See, which one am I going to go for? Because it takes a while to refocus and realign the cameras. That's the biggest thing.
Okay, I think we're going to have
Okay.
to bail out because we're going to be out of this room now.
All right. That's it.
Thank you.